I wanted to start out by saying thank you to the conveners today for the chance to come out. I was really excited to have the chance to talk to you about two of my favorite things. One was a bit of science history, and the other one is recent research that we've been doing in climate change. And so to get started, I wanted to really pick up where David left off, so I'm glad that I got to go after him. And I wanted to highlight the fact that David was talking about the atmospheric abundance of CO2, a known greenhouse gas, but he was looking at this in terms of many millions of years, looking backwards in time here. And in fact, what we have to do to start considering modern climate, which is the topic of this talk, we have to really zoom in on the far right-hand side here. So this is approximately the last million years. And David gave us this nice plot also from the Intergovernmental Panel on Climate Change of CO2 and temperature over approximately the last million years. And to get to the topic of this talk, we have to zoom in still further yet. So we're really getting out of this deep time to talk about the modern age right here. And something that's been written about at great length is the fact that you'll notice that human civilization has really taken off during just this period, which is a remarkably steady temperature as well as CO2 period in Earth's history. And that goes back to what Marcia and Lindy both mentioned about this correlation between human history, the fact that we're really at risk, not life as a whole. And so I think depending on where you get your news, some people may have a misconception that this idea of CO2 having an effect on Earth's climate is something that we've only recently gotten to. And that actually isn't the case. And as an experimentalist, this is actually one of my heroes. This is John Tyndall, who Sarah mentioned earlier. And Tyndall, in the mid-1800s, actually worked out the basics of greenhouse gases in the Earth's atmosphere. So Tyndall built what he called a comparative spectrometer, and this was essentially just a little tube here, and he was able to put different gases into this tube, and then he was able to pass different wavelengths of radiation, different sources of light through that to see what effect it was going to have. And one of the things that he noticed, which Sarah mentioned earlier, was that the major atmospheric gases, oxygen and nitrogen, had essentially no effect. You could pass different radiations through them, and there was very little change that he observed. But when he put in certain very low concentration gases from the atmosphere, and he highlighted CO2, ozone, and water vapor as those gases, he noticed that infrared radiation, the heat that the Earth was giving off, was trapped by those gases inside. And this is the basis for our understanding of climate change. And you might think that this is pretty interesting, and I think it's quite remarkable what one could build in the middle of the 1800s, but this was just basic science. And Tyndall was actually a step ahead of that, and this was what was really neat if you read his writings, is that he talked about how without these gases in the Earth's atmosphere, despite their low concentration, the Earth would be held in a frosty grip. And this goes back to what David talked about with snowball Earth. So it was already recognized over 150 years ago that not only were greenhouse gases important, but they were really necessary to life on Earth, to keeping the planet's temperature in the habitable zone that Sarah talked about earlier. And so then we're brought into this modern age. So we're starting to gain some understanding over 100 years ago of this. And then we have to ask ourselves what happened. And of course, Tyndall was alive really at the beginning of the Industrial Revolution as it was kicking off. And so since that time, we've been emitting CO2. And I think there's been some questions about this. But this is the Keeling Curve that Ralph mentioned earlier. And what you can see, this one starts in about 1950. This is taking off, and I'll show you where this was in Tyndall's time in a moment, but you'll notice that there's this variation, and this is the annual variation of photosynthesis on Earth, so peak when photosynthesis is most active, but then there's this underlying increase that's going on here. And if you were paying attention to the earlier curve, what you'll notice is that in 1850 or so, at the end of this sort of record here, we're at about 280 parts per million, and yet you look at this record, it's starting out even in 1950 over 300, and then I think as was mentioned earlier, we've shot by this 400 number late last year, and we've probably bid farewell to it. So we're on this sort of exponential rise that nobody really knows the form of. And so the point to get across here is that this is a lot more akin to what Lindy and what David were talking about in terms of these rapid events than it is the sort of orbital mechanics and the changes that you're seeing in CO2 and temperature that are going on here over the last million years. So at this point, we are now off the chart here. You would have to add on another 100, and we're something like up here. And so if you look at this Intergovernmental Panel on Climate Change report, I don't expect you to read through this whole thing, but they talk about the unprecedented nature, the unprecedented state that we're in with our atmosphere right now. Unprecedented in the sense of something that hasn't been seen over the last 800,000 years, certainly not in human history, and we're at a level of CO2 over this record that David talked about, something like 40% greater. So again, you might think that the basics of this may have been worked out, but that we're still very uncertain about what's going on and how this increase in CO2 may impact the climate of our planet. And this also couldn't be further from the truth. There was a scientist who was actually born the year that Tyndall was making his seminal measurements. This is Svante Arrhenius, who Rolf mentioned earlier. And Arrhenius was actually quite a remarkable character. So he won a Nobel Prize in physics, but one of his sort of side hobbies was being one of the world's first climate scientists. And so this is a famous quote attributed to him, and I can translate this into modern English, which is that there would be an associated temperature rise of the planet with a rise in CO2, essentially following on the experimental work that Tyndall did. What was really remarkable about what Arrhenius did is he did the first study of climate sensitivity. So climate sensitivity is generally acknowledged as this idea that you double CO2, and what effect could that possibly have on our climate? We have these inferences from these past climate states and these past records that David talked about, but Arrhenius really looked at the radiative transfer of the Earth's atmosphere, the measurements that were made by Tyndall to try to come up with this estimate. And he came up with quite an interesting estimate, and so this was the first acknowledged estimate of climate sensitivity, and Peter Stone in our department has looked at how this has changed over the years. But he said, what if we doubled CO2 and then the climate was at 280 parts per million? And he came up with that you would increase the temperature of the planet by about 5.5 degrees. And so I often get this question about how forward-thinking he was and that he was worried about global warming at this point in time. And that also couldn't be further from the truth. It turns out that he was mostly interested in this because if you'll recognize his name as being Scandinavian, he was from Sweden. And he was very interested in warming the climate up so that Scandinavia could become more fertile. So he was thinking about climate change in a completely different way than we do today. So how is Svante doing into the modern day? We now have the ability to sort of think about this climate sensitivity as the planet has changed over the period from the late 1800s. What David mentioned is this observational period over which time we've had modern thermometers and that type of thing. And this is also from the Intergovernmental Panel on Climate Change report, starting in about the year 1900. There are a few records that go back to the 1880s, and what we've seen is the temperature of the planet has risen in response to the increase in this greenhouse gas by something just under a degree. 0.85 degrees C is the generally held belief. It is higher over land, something on the order of 1.5 degrees C. If you look at the record, and Rob mentioned this or alluded to this in just the start, you have to update this on a yearly basis because last year was the warmest year on record, the year before that was the previous warmest year, it was the record that was beaten, and so on. And so I very often hear people say, our children or our grandchildren will be living in a world with a very different climate than the one that we have right now. That is not true. We are already living in a world with a very different climate. Right on this list, you have to get out of my teenage years to be in a climate state that was one that isn't on this record. So the 1990s and the 2000s fill up this entire record of the 20 warmest years on climate over that period of time. If you're paying attention, though, Svante's estimate of climate sensitivity is a little bit off because, as I said, CO2's gone up something like 40%, and he estimated that the temperature would go up with 100% increase, something like 5.5 degrees, and we're not really at that. So this brings into question, what is the real climate sensitivity, and why is this uncertain? Why can't you do it with something like a simple radiative transfer model? Why haven't we just pinned this down, and we can project perfectly into the future exactly what's going to happen with climate? And so this is where my own interest and my own research comes in. And so there's been a few images like this shown. I'm going to show one that Sarah showed just a moment ago. This is a real image of the Earth. This was something that was knit together by the Japanese Space Agency. So this is not a picture or any way a representation like that. But they've carefully chosen images to make this mosaic. And what's missing on this? Clouds and particles that are in the atmosphere, which Lindy started speaking of. And so at any one time, the Earth doesn't look like this unless you cherry pick the mosaic and the way to make it. The Earth actually looks something like this. It's covered maybe 30 to 50% at any one time by clouds, And some of that is not clouds, it's actually particles. It's dust storms, it's smoke plumes, and that type of thing. And the thing that immediately strikes you is that this is white, it's bright, and it's going to reflect sunlight back away from the planet. So what this implies is that a change in particles and any change in clouds in the Earth system is actually going to have the opposite effect from greenhouse gases. It's going to offset some amount of the global climate change, the global warming that we see because of a change in things like CO2, methane, and the other greenhouse gases that we've talked about. So I think for anybody that's spent any time in Southern California during the summer, this is a pretty easy concept to think of how particles might have an effect on the surface temperature. This is in Southern California. This is actually a picture taken of Singapore, which is where we have a joint institute with MIT as a joint institute. And this is from a couple of years ago. These are human-caused particles. This was a time of the year where they're starting to plant crops. So what they do is they go out and burn all of the slash that's left in the fields. They're also burning down forest area in order to make more land that can be planted with crops. That smoke plume then moved over the city, and this image is taken. What you immediately notice is that some of the sunlight that should be striking the surface of the planet and warming it is actually redirected towards the photographer. It's why the image looks blurry. And so that's energy that would otherwise be warming the planet that would be reaching the surface that isn't able to make it there because of the presence of these clouds that are in the way. So this is what we would term the direct effect of particles on climate. So more particles in the atmosphere, again, as Lindy alluded to, will reflect radiation back into space and thereby cool the surface of the planet, offsetting some of the global climate change or the global warming. So this is where I get to have some fun. I, with Kurt's permission, brought along a small experiment that I'd like to show you. I think everybody can get their head around how particles might affect the temperature, but not how particles can affect clouds and then affect temperature. So we're going to do a small experiment. As an experimentalist, I always get a little bit nervous when I can't get my hands dirty and do something. So we're going to make a cloud here. And we have all the basic ingredients. Hopefully you'll pick this up on my microphone. But we're going to build our cloud in this little chamber here. And so this chamber has all the ingredients necessary. It has a bit of water in the bottom, so the humidity in this chamber is about 100% right now. And this pump is going on because what we're going to replicate is a cloud that's forming over the open ocean. It's going to be like a parcel of air moving up, something that Carrie may be talking about later, as due to convective activity. The pressure is going to drop, the temperature is going to drop slightly, the relative humidity is going to go over 100%, and there's going to be a cloud that forms in the chamber. And so I'm putting my finger over this because you can hear the pump going on, and when I take it off, you can hear the suction of air through. So the pressure in this vessel is dropping, probably to something like 50% of atmospheric pressure. And at this point, you have to doubt that your speaker knows what he's talking about because there's no cloud forming in this chamber. And you guys can verify that if it can't be seen in the back. But I think it's actually quite good. We tested this out on the black background. The reason that there's no cloud forming in this chamber is that this is a small filter. And there's no particles in the chamber because it's been pumped clean. There's no seeds for a cloud to form on. And so I've brought some particles along with. I'm not going to light up a cigarette. I actually did this for a reason. We could bring in some mineral dust and sprinkle it in if we wanted to, but we were just talking about biomass burning aerosols and their direct effect. We're going to now look at biomass burning aerosols from this lit match, the smoke that comes off of it, and the effect that they can have on cloud formation. So to do this, we're going to start our forest fire, in this case, and now we're going to put particles into the chamber, and then we're going to look at what happens. So there's the particles going into the chamber, and we drop the pressure just like we did before, and I think you guys can see against that black background, now we have a cloud form in it. We can let that cloud go. We're going to form another cloud. I pumped some of those particles away, so there's less now. And what you may not be able to see is the optical properties of this cloud are changing as we do this. Each subsequent cloud has less particles to form on. It's becoming less and less bright, less and less white, less and less able to reflect radiation, in this case, back to space. And we could even keep doing this for quite a while, but we'll stop at about 4 cloud cycles and then continue the talk. So the point to be made here, the one that's interesting for us from a climate standpoint, is this is really the area of uncertainty in our current understanding of climate. We as humans are putting some particles into the atmosphere. What effect do they have on clouds, their occurrence, their frequency, their location, as well as their albedo, their brightness, their ability to reflect radiation back into space? And this is what we're doing in our group right now, is trying to understand that. It's not as easy a problem as you would think, and it's certainly not one that has been tackled since the 1850s. This is the current state of climate research, and it does limit our ability to project climate change through models into the future, is understanding this formation of clouds. To do this properly, we need to gain access to clouds. We do this typically through research aircraft, as well as getting to mountaintop sites. We've developed instrumentation to separate the droplets and the ice crystals that form those clouds out of the clouds. We then evaporate it. We can bring some of the particles, those seed aerosols, back to MIT to look at what their composition is and what influence we as humans might have had on them. We can also do this with instruments that we fly on those research aircraft or bring to those mountaintop sites. And so what we find is a whole host of particles that can't be natural, that are really due to our activities as human beings that form these clouds. And so these are just some examples. These are zinc oxide particles and tin particles mixed with black carbon, things that are emissions from anthropogenic, from man-made sources, probably industrial activities. And this is one of the ones that we've been spending a great deal of time on. This is a natural particle, which is mineral dust with a bit of lead on it. And that lead's really interesting because that's a leftover remnant of tetraethyl lead, the leaded gasoline that we were burning in the States until the 70s and the early 80s. And it's found its way onto the surface of the planet. It's adhered to some of the dust there. The wind comes by, picks it up, and we have these mineral dust particles that now have an anthropogenic component. And the point that I'd like to make in closing is that this is something that's extremely difficult to model. It's something that isn't in our current generation of climate models. This is something that we really have to understand to get our projections right moving into the future. And so I'm just going to close with this now famous slide, which comes from the Intergovernmental Panel on Climate Change report, where the scientists that put this together added up what all of the different human activities, their effect could have on climate. Things that fall to the right here are warming agents, so you'll notice CO2 and the other greenhouse gases are potent warmers. And then what you'll see is that clouds, particles, and the clouds that they spawn have this offset, this negative impact towards global warming. They offset some of that warming. If you add everything up, it's still positive. It was somewhat positive in the 50s, somewhat more positive in the 80s, and quite a bit more positive in the decade in which we live right now. But the take-home message that I'd like you to realize is that the error bars here are actually quite small. Our understanding of greenhouse gases is longstanding, since the 1850s. The error bars here on particles, as well as clouds, are much, much larger. And this is one of the things, along with what you'll hear about later, some of the concepts from the ocean, as well as ice sheets and so on, are what really, in the current day, are limiting our certainty in climate change and the projection of that moving into the future. So with that, I'd like to say thank you for your time. I will not stand any more in the way of the coffee break, as Rob pointed out, but thank you.
Very nice. We have a few opportunities for questions for Dan.
Down the planet. Your uncertainty bars are very big there. I imagine that holds that the sulfates be put in artificially as well.
Yeah, so the question is regards a geoengineering solution, which is this concept of doing something to the climate system to offset global warming. I'll point out that Svante Arrhenius was in favor of geoengineering back in the late 1800s in a very different way. But one of the proposals has been to add aerosols or augment clouds in the atmosphere to set this off. I personally think that this is a horrendous idea, and as you pointed out, it really has to do with the error bars. It's a bit like those old stereos that we had where you had sort of the coarse and the fine adjustment. If you're going to tune climate, it doesn't seem like a good idea that you would go after the most uncertain aspect of climate as the tuning element. You would want to go after the most certain one. So from that simple standpoint, it doesn't really make sense, but it is also fraught with other things. Ocean acidification continues unabated. There's changes in precipitation as a result of changing clouds and aerosols. So there's a whole host of reasons why adding aerosols and clouds is a bad idea. But you're absolutely right. This uncertainty should immediately cause anybody considering that to take pause.
Not to mention the geo-health issues. Question?
One of the most serious uncertainties is the distribution of additional clouds between cirrus and cumulus. What can you say about that?
Yeah, so the question is what clouds, to paraphrase, what clouds are most important? And you're absolutely right. Low-level clouds are fairly well understood. We've worked out the mechanics of so-called warm cloud formation or droplet formation fairly well. Ice clouds, high-level clouds, cirrus clouds, all the same topic, are also reasonably well understood in the climate system. There's aspects of it that we're working on right now to try to work out. Where we're failing are so-called mixed-phase clouds, the ones that are droplets and ice, the ones that live in between those two areas. And I think that that's where the current research is at. It's why we've developed a number of mountaintop sites recently so that you can get into these clouds and try to study them for long periods of time and see what the effect of human activities on those particles is and how they might be changing. So I think that is, if you added up all the uncertainties, mixed phase clouds I think are one of the most poorly understood, and we could talk for hours about why that's the case.
I'll take one more question. Far back.
Doesn't it matter whether the clouds are in the daytime or nighttime?
Yeah, so the question is, does it matter daytime or nighttime? It absolutely does, because I think this was alluded to earlier. Sarah may have mentioned this, but clouds are complicated. This is saying that for the most part, their effect is on reflecting sunlight back into space, but they also have a component of being able to absorb outgoing terrestrial radiation, which would take place at night as well as during the daytime, and send that back. So this is integrated over a day, but you're absolutely right. The diurnal cycle in that and their presence at one time or another would be very important in understanding the full radiative transfer.